السلام عليكم ورحمة الله وبركاته. Yeah, Allah willing, today we are going to complete chapter 3. It took us so long. Chapter 2 and 3 are extremely long, and yet they are very, very important. Okay. Chapter 2, we looked at fluid properties. Okay. And then chapter 3, we looked at fluid statics. In chapter 4, we'll start to deal with fluid kinematics. Okay. So let's move on. I'd like to expatiate, although we did this, but introduced these two slides. After that, we will move on to where we stopped in the previous lecture. Okay. So let's briefly discuss these two slides. This one. All right. Still on floating and immersed bodies. Remember this, that the body floats when its density is less than the density of the fluid, and it becomes suspended in the fluid if the density of the fluid is equal to the density of the body, and then it sinks to the ground, to the bottom of the fluid if it is heavier than the fluid. In other words, the density of the body is greater than the density of the fluid. Okay? These are the conditions. Okay? Now, we have, let's say, a ship, okay, which is loaded. Okay, the shaded area shows the submerged area. Okay, when it is loaded here, we have, let's say, W1 or WS1. That is the weight of the solid or the weight of the ship. Okay, WS1. In the second case, we have WS2, which is greater. When it is loaded further, it sinks further. When it is loaded further, in the third case, it becomes completely submerged. Okay. When it is loaded further, then it sinks to the ground, to the bottom. Okay, it sinks to the bottom of the sea. Okay. Now, the first instance is one. It floats. It is floating with part of its volume submerged. Okay. In that case, the density of the body, which is the density of the ship, okay, is less than the density of the fluid. In this case, water. Okay. That is this. Okay. And then the weight of the ship is less than the weight of the displaced liquid. Okay. This is the volume displaced, indicated by the shaded area. This is the volume. If you have it this way. So this is only the volume of the displaced liquid, while the volume of the ship is the total volume. Okay. So the weight of the ship. Okay. We are coming to that. The weight of the ship is less than the weight of the displaced volume. That is why it is floating. Okay? But when you look at the equilibrium of the ship, okay, because it is static, it is at equilibrium. you have the force, the weight of thrust FD1 acting. It is the only force supporting the weight. So FD1 is equal to the weight of the ship, okay, in this case. And if the buoyant force is equal to the weight of the ship, okay. Now I put it D, but I will change it to B, okay, to indicate the buoyant force, okay, active. So the weight of the fluid, the buoyant force is given by rho g times the volume of the displaced liquid, okay? And the weight of the ship is given by rho g times the volume, the total volume in this case. It is the total volume of the ship, okay? And if these two are equal, you see g will cancel g because it's constant, okay? Rho f is greater than rho s1 according to this, okay? If rho s is greater, then definitely Vt must be greater than Vd1, okay? And it's obvious here. That is the volume of the displaced liquid is less than the volume, the total volume of the ship, okay? This is the volume of the displaced liquid, okay, indicated by this, okay? While this is the total volume of the ship, okay? So now, in the second instance, you have the weight to be increased, the weight of the ship, by adding more load on it, okay? So you have WS2. Now, the buoyant force increase as well, okay? FD2. Because the body is still floating, the ship is still floating, okay? Except that the weight has increased. So the buoyant force has increased. In this case, the buoyant force here in the as indicated even by the arrow, okay? Even in this case, the buoyant force is still, the weight of the ship is balanced by the buoyant force. That is why it is still floating. And again, the density of the ship is still less than the density of the fluid. Again, that is another reason why it is still floating. Okay, so even in this case, the volume of the displaced liquid is less than the total volume of the ship. Okay, as we can vividly see. Now, when you load it further, but in this case, yeah, like I mentioned, the weight WS2 is greater than WS1, okay, which implies that the buoyant force in the second case is greater than the buoyant force in the first case. And if you look at it very well, vividly, the displaced volume is also greater than the displaced volume in the first case. So VD2 is greater than VD1. Okay. Now, when we go to the third case, the ship is loaded further, so it is going to sink. Okay, it is completely submerged. Okay, in the water, and here you have FD3. Okay, at this point, because it is submerged, completely submerged, the density of the ship is equal to the density of the fluid. Okay, and in this case, you have the buoyant force being equal to rho g and the volume of the displaced liquid. Okay, which is equal to the weight of the displaced liquid. Okay, in this case, the buoyant force is equal to the weight of the displaced liquid. And the weight of the displaced liquid now is exactly equal to the volume of the displaced liquid is equal to the total volume of the ship. You can see, because in this case, the ship is completely submerged in the water, okay? Unlike in this case, in which part of the volume of the ship is floating, okay? Like in this case, okay, in which part of the volume of the ship is floating. But in this case, the ship is completely submerged. So the volume of the ship, the volume of the displaced liquid, in this case, or fluid, is equal to the volume of the ship. Okay, so that's why we have VD3 to be equal to VT. While in the previous cases, the volume of the ship is greater than the volume of the displaced fluid. but the weight of the ship is less than the weight of the displaced fluid. Okay, while in this case, if it is completely submerged and within the body, within the fluid, okay, FD3 is equal to rho g Vt. Okay, but remember Vt is equal to Vd3. Even in this case, when it is just completely submerged, okay, because Vd3 is equal to Vt, so we can replace Vd3 here with Vt. And remember, the densities are equal, so we can replace rho F with rho S3, okay, the density of the ship. Okay, and when we do that, we will have the buoyant force to be equal to this. And this is exactly equal to the weight of the ship. Okay, so when it is completely submerged, the weight of the ship is exactly equal to the weight of the displaced volume. Okay, it's equal to the weight of the displaced fluid when it is completely submerged. Okay, and then in this case, the buoyant force has reached maximum value. FD3 is greater than FD2. Okay, but then FD3 cannot increase any further. This is the maximum value it can attain. Why? Because at this point, it can support the total weight. Okay, the total weight of the ship is completely supported by the buoyant force. Okay, so once the weight of the ship increases further, the buoyant force remains the same, and as such, the buoyant force cannot be supported by the ship cannot be supported by the buoyant force, so it cannot hold it in place. And that is why in the fourth case, the ship sank to the bottom because the weight has increased in this case. Okay, so in the third case, like I mentioned, F, the buoyant force is maximum. It has attained its maximum value. The third case is greater than the second case. The second case is greater than the first case. Like I made an analogy with the frictional force. You see, in this case, the buoyant force increased gradually from 1 to 2 to 3. Okay, and it increases because of the increase in the weight of the ship. As the weight of the ship increases, the buoyant force increases. It's just like you holding something, holding a weight, isn't it? W. Okay. W will be acting on your palm. So there will be action and reaction are equal and opposite. Weight will be acting on your palm while you are holding the weight, but you will feel exactly the same weight, W. Okay. When W increases, let's say W2, you will have to apply W2 to hold this weight in place. Okay. W2, this weight has to be balanced by your weight, by the force exerted on your palm. Okay. Your palm has to be strong enough to hold W2. Okay, that is, in other words, it has to exert equal but opposite reaction. If the weight is greater than the force that your palm can support, then it will bend your palm down, isn't it? It will bend it down and the weight will fall to the ground because your palm can no longer support the weight. That is exactly what is happening here. When the weight increases, after the third case, when the weight increases further to WS4, WS4 is greater than WS3. The buoyant force at this point, it has reached the maximum value. So it can no longer support the weight of the ship. So the ship now will overcome the buoyant force and it will go to the bottom of the sea. Okay, so here there must be extra force to support it, which is the reaction coming from the bottom of the sea. In addition to the buoyant force, there will still be buoyant force acting on the ship, but the buoyant force is not enough to hold it in place, to hold it, completely suspended in that fluid. Okay, so the buoyant force need like a backup, like a reinforcement from the bottom flow, from the reaction coming from the flow. So at this point, the ship is also in equilibrium, but acted upon by the buoyant force of this plus the reaction coming from the bed, okay, from the bottom of the sea or of the container or whatever. Okay, So that's why in the first case, and in the fourth case, again, the density of the ship is greater than the fluid. That is why it sinks, because it is heavier. So it has higher density than the density of the fluid. Okay, and the buoyant force in this case is we'll later change the designation, the symbol. Instead of FD, I will use FB to indicate the buoyant force. Okay, so here the buoyant force is no longer equal to the weight. Okay, it's no longer equal to the weight. Whereas in the first, second, and third cases, the buoyant force is exactly equal to the weight of the ship. In the fourth case, the weight of the ship is greater than the buoyant force. That is why the ship sank to the bottom. Okay? And when it sank to the bottom, the weight of the ship is greater than the weight of the displaced fluid. While in the third case, the weight of the ship is equal to the weight of the displaced fluid. Okay? But when it sank to the bottom, because of the fact that the density is greater, the density of the ship is greater than the density of the fluid, then the weight of the ship is also greater than the weight of the displaced fluid. Okay? So you need, and like I told you, FD3 and FD4 are equal. Okay? FD3, the buoyant force in the third and fourth cases are equal. I told you in the third case, it is maximum. Okay? And it will maintain this maximum value until it is overcome in the fourth case. In the fourth case, the weight of the ship, is so great that the buoyant force can no longer support the weight of the ship, and that is why it sank to the bottom. Okay, so these equations will help you in solving a lot of problems dealing with floating and immersed bodies, and it will help your understanding as to the exact meaning or the interpretation of the Archimedes principle. Okay, simply, which can be defined now simply as, whenever you have a body, immersed in fluid, it experiences an upthrust or buoyant force which acts vertically upward, and the buoyant force is equal to the volume. Okay, is equal to the weight of the displaced fluid. So you can define it that whenever a fluid, is immersed partly or fully in fluid, it displaces volume. Okay, it displaces its own weight in the fluid in which it floats. It displaces its own weight, or it displaces its own volume in the fluid in which it is immersed. In the third case, the ship completely displaces its own volume. Okay. In the third case also, it displays its own volume completely. That is why the volume of the ship is equal to the volume of the displaced fluid. Okay, and the volume is the same in the third and the fourth case. Okay, it's the same, but of course, this is less than this and this is less than this. But 3 and 4, the volume of the displaced liquid is equal. Okay, the volume is equal in both cases. Okay, so you can define Archimedes principle in so many ways. Okay, but you should understand that when a body is floating, then it is not displacing its own weight. I say it's not displacing its own volume completely. It only displaces its own volume if it is completely submerged. That is in the third and the fourth case. That is when Vt is equal to Vd4, and Vt here also in the third case, Vt is equal to Vd3. That is the volume of the ship is equal to the total volume of the ship is equal to the volume of the displaced fluid. Okay. So now this is another diagram to buttress the point. A floating body, you can see here, it weighs less than the fluid it displaces. Okay, it weighs less than in the first instance because it's floating. You can see only a small portion is submerged. This is the submerged area. Okay. In the second case, it sank to the bottom. You can see here the buoyant force is greater, somehow, bigger than the weight. It's not, for equilibrium, it is the same as the weight, but it goes to tell you that it can attain a maximum value. It can increase, okay? And it will increase up to this point when it is completely submerged, okay? So this is where the buoyant force is maximum, and in this case, the body, when it weighs the same as the fluid it displaces. In the third case, the weight of the body is equal to the weight of the fluid displaced. In the third case, when it sank to the ground, you can see the buoyant force smaller than the weight. Weight is the gravitational force acting. Okay, it is the gravitational force acting on the body. So in this case, the gravitational force is greater than the buoyant force. Okay, so that is why it pushed it downward. It sank to the bottom. And here you still have the buoyant force acting, but in addition, for this body to be supported on this interface, there must be reaction, because action and reaction are equal and opposite. So in this case, that is the fourth case here, in which we'll say now WS4 has to be equal to the buoyant force in the fourth case plus the reaction which is emanating from the bottom. Okay, so this reaction has to be there to support the buoyant force so as to be able to hold the weight of the ship in place. Okay, because if they are not equal, then it means the ship will also, pass through the bottom. Okay, it will go deeper. But if it is holding it in place, meaning equilibrium is maintained, then WS4 is equal to FD4 plus R, where R is the reaction coming from the bottom of the container or the seabed or anything that is applicable. Is it clear? Now, our concept of crease. In a situation whereby an object sinks to the bottom of a fluid in a container, like in the fourth case, which implies that the force is not enough to balance the weight of the object. What other force is required to balance the weight of the object for equilibrium? Like in this case, where it sank to the bottom, okay, you have the buoyant force here acting, okay, you have the weight. So we are saying that the weight is greater than the buoyant force, okay, but the body is in equilibrium. So what other force is required to hold it? Okay, that we need what? Reaction from the bed. Okay, we need so that the weight will be balanced by the buoyant plus a reactive force. Okay, coming from the bottom. Okay, to support the buoyant force in order to maintain the object in equilibrium. So now we can move on to the where we stopped in the previous class. I was explaining. I think I was explaining the stability of immersed bodies now. Okay, trying to explain the neutrally stable, unstable, and the stable states. Okay, we already explained this. When it is bottom heavy, the rotational disturbance, will still bring it back because of the because of the restoring moment. Okay, and then if the center of gravity is coinciding with the center of buoyancy, so it will be neutrally stable. Okay, it can be moved to another location, but it will remain in equilibrium in the new location. Okay, so for this case, no tendency to overturn. So for such bodies, there's no tendency to overturn. An immersed neutrally body is stable if G and B are coincident. Okay? And an immersed body whose center of gravity is directly above B is unstable, like in the third case. And any disturbance will cause this body to turn upside down. If it is this way, okay, that is the center of gravity is above the center of buoyancy. So this is unstable. Okay, it may be in equilibrium now, but any slight disturbance, any disturbance, okay, will cause the body to turn upside down. Okay, so it will push it either this way or that way. because the center of gravity is higher, is way above the center of buoyancy. So here is unstable if G is directly above B. And what does it tell you? The lower the center of gravity, the more stable the body is, isn't it? The lower the center of, like in this case, you see the center of gravity is lower. That's why it is stable. In this case, the center of gravity has increased to coincide with the center of buoyancy, so it is still stable. But when the center of gravity now goes up again, in this case, now it becomes unstable. Because all the time bodies, they want to attain equilibrium. And to attain equilibrium, any slight disturbance will now distort the equilibrium condition. I mean, it will now push it either to the left or to the right. And then it will become at equilibrium with the weight acting down and with the center of gravity now lowered. So it will become something like this, okay? So it will attain stability. All bodies try to attain equilibrium at all times, okay? Now, what about a case where the center of gravity is not vertically aligned with the center of buoyancy, like in this case, okay? The center of gravity is not aligned with the center of buoyancy. In this case, it is not appropriate to discuss stability for this case, since the body is not in a state of equilibrium. In this case, because the sum of moment is not equal to 0. If you take moment about B, the weight will have moment about B, because the weight is separated by a perpendicular distance, okay? Of course, again, the buoyant force will have moment about G, because it has a perpendicular distance with respect to point G, okay? So the total weight, the total moment in the system is not equal to 0 in this case. So all the time, there will be restoring moment that will take it back to equilibrium condition. And equilibrium condition is when the sum of moment equals 0. And it will only be 0 when the center of buoyancy and the center of gravity are aligned. When they are aligned, then both the weight and the buoyant force will have no moment, okay? Their moment arm will be 0. Hence, total moment acting on the body will be equal to 0. And that is when the system is in equilibrium, okay? Or that's when the object can be said to be in equilibrium. So in this case, definitely there will always be restoring moment. Like in this case, the moment will be towards this. It will be counterclockwise. It will push it until it attains stability, like in this case. Okay? So the restoring moment is counterclockwise and causes the body to rotate clockwise so as to align the point G vertically with point B. Okay. Note that there may be some oscillation, but eventually the body settles down at its stable equilibrium state. Okay, meaning case 1, it will attain case 1. There may be some oscillation, but over some time it will have to it has to attain equilibrium. Okay, the initial stability of the body of figure 352, which is this one, is analogous to that of the ball on an inclined flow. You remember we talked about ball on an inclined flow, which we said it is not in equilibrium because as soon as you release it, it will definitely move. So it is not in equilibrium. Ab initio. Okay. So like I mentioned before, what all these figures are telling you is that the lower the center of gravity G, the more stable the body is. Okay. And that is why even cars that are more stable, you realize they have their center of gravity lower to the ground, okay? Lower to the ground level, okay? So whenever a car has center of gravity lower to the ground level, you realize that it becomes very, very stable, okay? Now, attention quiz. Can you predict what would happen if the weight in the body of this figure were on the opposite side of the body? Meaning the weight is here. Instead of here, it is here. Okay, so what will happen? What will happen to the restoring moment? Is it still going to be counterclockwise? Is it? No, in this case, it is going to be clockwise. The restoring moment is going to be in the other direction. Okay, this is exactly what will happen because the weight is towards this side. Okay, so it will push it towards the right. Okay, that is clockwise moment. Now, still on the stability of floating bodies, here we'll briefly look at ships again. Okay, the rotational stability criteria are similar for floating bodies. Again, if the body is floating, if the floating body is bottom, and thus the center of gravity is directly below the center of buoyancy, the body is always stable. Like in the first case, this is a ship. Okay, this is a ship. You have the center of gravity below the center of buoyancy, so it is always stable. Okay. But unlike immersed bodies, a floating body may still be stable when G is directly above B. You saw that here, when G is above B, when G is above B, it is unstable, isn't it? For immersed body. But for floating body, it can still be stable, okay, when G is above B. Okay, when G is directly above B, okay, it can still be stable. And this is because the centroid of the displaced volume shifts to the side, okay? Like when you look at the second case here, you have G to be above B, okay? But the ship has tilted slightly. It has tilted, okay, slightly. And the B has a new position, okay? The center of buoyancy has a new position in this case. The volume shifts to the side to a point B prime during a rotational disturbance, while the center of gravity G of the body remains unchanged. Okay, center of gravity G of the body remains unchanged. If point B is sufficiently far, these two forces create a restoring moment and return the body to the original position. In the second case, you can see G to be above B. Assalamu alaikum. Yes. I'm in a class.
When are you done with your class?
At 8:50.
So, is your lecture recorded?
I'm recording.
Okay, Doctor, thank you.
Yeah, welcome. Sorry for the slight digression. So now in this case, you have center of gravity above the center of buoyancy, yet the body is still stable, because if B is sufficiently far, these two forces, you see, B and G are not aligned, so there is restoring moment created, which is counterclockwise, which will bring it to state A, okay, to the stable state A. Okay, as it is here, it is also stable. When you tilt it, this is the original centroid, okay, where the center of gravity is passing through, and this is the center of buoyancy, the new center of buoyancy, because the center of buoyancy is the center of the displaced volume. Okay, it is the center of the displaced volume. Okay, so that is why in the second case, the center of buoyancy becomes B prime, not in the same position as before. Okay, because the displaced volume, the shape of the displaced volume changes. Okay, now a measure of stability for floating bodies is the metacentric height, GM. You see here, G and B prime are not aligned. Okay, but B prime is acting, when you project it vertically up, is intersecting with the axis coming from the center of gravity at point M, which is called the metacentre. Okay, and GM is called the metacentric height. Okay, that is G, from G to M is the metacentric height, which is the intersection point of the lines of action of the buoyant force through the body before and after rotation. This is before rotation, isn't it? Where G and B are all aligned along the same line of action. But when it is rotated, okay, when it is slight, when there is slight rotational disturbance, okay, B is shifted. The line of action of B is changed. Okay, so the point of intersection here is the metacentre, and GM is the metacentric height. Okay, a floating body is stable if the body is bottom heavy, and thus the center of gravity is below the centroid of the body, is below the centroid B of the body, like in the first case, or if the metacenter M is above G. If the metacenter is above G, it is also stable. Or we can say if GM is positive, although we are going to mention in this case, GM is greater than 1. That is positive. Okay, because GM here is positive. But when GM is negative, it is unstable. That is less than 1. This is stable, this is unstable. Okay. So if the metacenter M is above G, however, the body is still unstable if G is below. Like when it is pushed further, when the rotational disturbance is increased over turning moment, because when you push it further, B will, the intersection will now be here. Okay, so M will come here, and GM is now negative, or M is below G. So this is unstable because there will be overturning moment. Okay, so G weight will have moment about point B. Okay, and this will now capsize the ship. Okay, so this is an unstable condition. The metacenter may be considered to be a fixed point for most hull shapes. Hull, is what part of the ship, that is sometimes floating and sometimes, partly immersed in the water. Okay. So for most shapes, for small rolling angles up to 20 degrees, typical values of metacentric height are, for cruise ships, you have 0.3 to 0.7 meters. For sailboats, you have it higher, 0.9 to 1.5. For cargo ships, you have 0.6 to 0.9. And for warships, you have 0.75 to 1.3. Okay. So a floating body is stable if M is above G, this we mentioned, and thus GM is positive. I explained this. It's positive if it is greater than 1. And because GM is a displacement, if we look at it as displacement, then displacement can be positive or negative, unlike distance. Distance is a scalar quantity, while displacement is a vector quantity. Okay? And unstable if M is below G, thus GM is negative. In the latter case, the weight and the buoyant force acting on the tilted body generate an overturning moment instead of a restoring moment. The restoring moment is the moment that will take the body back to a state of stability, while overturning moment is a moment that will lead to the ship to capsize. Okay, will turn it upside down. And the length of the metacentric height GM is a measure of the stability. The larger it is, the more stable. It is the more stable is the floating body. So here, larger values of the metacentric height implies that warships, are most stable. Of course, they should be designed to be and sailboats. Okay, sailboats highly, because they have higher GM values. And as already discussed, a boat can tilt to some maximum angle without capsizing. It can tilt to some maximum angle without capsizing. But beyond that angle, it overturns and sinks. Okay, it can capsize to some maximum angle, to this angle. Okay, so this angle is equal to that. Okay, this angle. So it can tilt to a maximum angle, but beyond that angle, like in the third case, when the angle increases further, then it creates an overturning moment here. Okay, it creates an overturning moment. So still on the metacentric, metacentric height again. Let me. In this case, you can see BM, BG. Okay. Okay. I'll there. Here you have an object. Center of gravity is G. Okay, the weight W acting, which is the weight of the body acting through G. And you have B, the center of buoyancy. And it is tilted by a rotational force, okay, rotational disturbance. You have G, okay, but the center of buoyancy is shifted, you can see, because in this case, the center of buoyancy is the centroid of this shape, centroid of this rectangular shape, which is here. But when it is tilted, the centroid of this immersed shape, which is here, will shift to somewhere here, okay? So the metacenter is the action of the buoyant force to intercept the original vertical axis when a body is given a small angular displacement. So when it is like tilted, okay, so this is G, and then this is the buoyant force, okay? So this is where they meet, okay? And then when you look at it, this is BM. We say it's displacement, so this is BM, this is BG, and this is GM, okay? So recalling our resultant force, you know, chapter 2 of vector algebra in statics. So BM is the resultant side, okay? So BM is simply equal to BG plus GM. Okay, in some text, like in the text you're using, instead of G here, they may use C. Okay, so you have BM equals CG plus CM. So the metacenter is determined by conducting an experiment on the floating body, and the BM, which is the distance between the metacenter and the center of buoyancy, is given by I over V. I is the moment of inertia, the horizontal section of the floating body. Okay, the horizontal section of the floating body at the free surface of water, at the free surface of water about a longitudinal axis. Okay, where V is the volume of water displaced by the ship. So V is not the volume of the ship. Okay, it's the volume of water displaced by the ship. So it is more or less like VD. Okay, VD. So the volume of water displaced by the ship. Okay, underwater. Okay, so remember this. So it is from this. So GM is now BM minus BG. BM minus BG. Okay, and BM is given to be I over V. Okay, so here we can find GM. There are three types of equilibrium for a floating body, which we explained: the stable equilibrium, which will return to its original position in the first case; the second case, unstable equilibrium, which do not return to its original position. Okay, it overturns, it capsizes; and the third case, which is stable equilibrium, which is neutral equilibrium. The body remains at new position and at rest. Okay, like in this case, it remains in its new position but at rest. Okay. Explain that if GM is positive, it is stable. If it is negative, it is unstable. Stability conditions. When M lies above G, like in this case, M is positive. And when M lies below G, it is unstable. Okay, and this we have shown with the ship figure. Okay. And G and when M and G coincides, M and G coincides, we have neutral equilibrium. Okay, and in this case, the metacentric height GM is 0. Okay, and M and G coincides, we have neutral equilibrium. And this is a very simple problem which I would like to take us for the next 5 minutes. Okay, to demonstrate the stability of a block. Here you have a block of wood 30 centimeters square. Okay, so this is the end view, 30 centimeter by 30 centimeter. This is the side view. The length is 60 centimeter and weighs 318. So the weight is 318. So it is a block. Okay, so meaning it is solid block of wood. Okay, will the block float with sides vertical as shown? So is it going to float as it is with sides vertical? So let's test. It is a block of wood is floating in water, and the goal here is to determine the stable configuration of the block of wood. So how do we go about solving, approaching this problem? We have to apply force equilibrium to find the depth of submergence. With the depth which it is submerged, okay, the depth of submergence, we need to find it, okay, and then we have to determine if the block is stable about the long axis by applying equation 3.47, okay, and if the block is not stable, we have to repeat steps 1 and 2, okay. So to find D, because it is floating, remember it means that the upthrust, the buoyant force acting, is equal to the weight of the block, isn't it? Okay. So buoyant force is equal to the weight. So that implies when you take this to the other side, minus W plus FB will be equal to 0. Okay, so summation of forces in the vertical direction to be 0. Okay, so FB positive, W is negative because it is opposite to FB. Okay, so what is the weight? The weight is already provided. What is FB? The buoyant force. The buoyant force is simply, as we know, gamma, then times the volume of the displaced liquid. Okay, and what is the volume of the displaced liquid? It is going to be the volume of the block that is submerged here, okay, that is submerged. And what will be the volume of the submerged portion? It is going to be the cross-sectional area, times the length. Okay, so the cross-sectional area is going to be D times, here is 30, which is 0.3, times the length, which is 0.6. That's why we have it this. So this is the volume. So here we can find D. So it's simply 18 centimeter, meaning the wood is submerged to a depth of 18 centimeter. Remember, the total depth is 30 centimeter. So it is submerged above half, more than half of the depth. Okay, because half of the depth will be 15 centimeter. We have 18 centimeter to be submerged. Now we can analyze the stability condition, okay, in the longitudinal axis by applying the formula GM equal I over V minus CG. This V, like I explained, is the volume of the displaced fluid. Okay, it's not the total volume of the body, but it is equal to the volume of the displaced fluid. Okay, it's rectangular, so the moment of inertia is VD cubed over 12. Okay, and the volume of the displaced liquid is going to be the volume of the body given by D. Okay, so it is going to be 18 times 60 times 30. We are not going to use the total volume, with the volume of the displaced fluid, and the volume of the displaced fluid is equal to the volume submerged, of the volume of the body submerged, the submerged volume. Okay, so that's why we use D, and that is why we found D at the beginning. Okay, and then what is the CG now? CG now is distance between the centroid. C is the centroid. C is the centroid, and G is the center of gravity. C is the center of buoyancy. Okay, C is the center of buoyancy. Okay, so how do we find CG? For the body, G is the center of gravity of the block, okay, which will occur at midpoint. Okay, for the block at midpoint, okay, it will occur at midpoint. As you can see now, this is 30. Okay, the centroid here is half of D. D is 18, so half of D will be 9. Okay, so center of buoyancy, which is C, is 9, and the centroid of the body, okay, the total height is what? 30. It will occur at midpoint, which is 15. Okay, which is even not inside water. So this is, so G will occur somewhere here. Okay, and this is C. So this from here to here, this is 9, and from here to here, this is 15. So what is CG now? Okay, and again from here to here also is 15. It's going to be 15 minus 9, okay, which is CG. 15 minus 9. And we can see GM is negative, meaning it is unstable. So it cannot float with its side vertical. Oh, the time is up. Tomorrow we will just finish this and then we start the next chapter. Okay? Any question? All right. Yeah, someone is asking M2 from where to where? From where we stopped, that will be from where we stopped, because major 1 covered up to pressure, up to just pressure, chapter 3. So from the subsequent chapters up to where we will stop in the before the major. Okay, from topics after pressure. Okay, because chapter 3 we started with pressure, you know, atmospheric pressure, dam pressure, and the manometric determination. You know, so it will be after pressure. All the topics after pressure. Okay, so see you tomorrow.